Today, we're going to pull back the curtain on a piece of technology you rely on every single day, probably without even thinking about it. We're talking about the thermal power plant. We're going to break down exactly how these enormous facilities turn plain old heat into the electricity that powers, well, everything. So, why are we focusing on this one type of power plant? Well, check this out. This one technology, in its various forms, is responsible for generating nearly half of all the electricity on the entire planet. It is an absolute workhorse, humming away in the background of our modern lives.
So how does it actually work? The core idea is surprisingly simple. You use heat to create motion, and then you use that motion to generate electricity. And the key ingredient that makes it all happen? One of the most common things on Earth: water.
When you really get down to it, this whole massive, incredibly complex facility has one and only one objective: to spin the shaft of a generator. And the machine that does all that spinning is the real heart of the power plant, the steam turbine.
Okay, so to understand how all these parts connect, we need to look at the basic process. It's a simple, repeating loop called the Rankine cycle, and it's basically a four-step dance between physics and engineering.
These four stages create this perfect, continuous loop. You've got high-energy steam from the boiler spinning the turbine. That now-used steam gets cooled back into water in the condenser, and then the pump sends it right back to the boiler to start the whole cycle over again. It's a closed system, designed to just keep on running.
Now you might be asking yourself, hold on, why go through all the trouble of condensing the steam back into a liquid? Why not just, use a compressor to raise the steam's pressure directly? And the answer comes down to one word: efficiency. Compressing a gas, like steam, takes a massive amount of energy. It is way easier to increase the pressure of a liquid. This one engineering choice is absolutely crucial to making the whole cycle work in the real world.
So we have a cycle that works, but in the world of power generation, just working isn't really good enough. It has to be powerful, and maybe more importantly, it has to be efficient. And the basic Rankine cycle, all by itself, well, it just doesn't cut it. And this brings us to the central problem that engineers had to solve. How do you take this simple, elegant loop and squeeze every single last drop of energy out of it? How do you make it better? A plant running at only this basic cycle would have really low efficiency and a pretty low capacity for generating power. A ton of the heat energy from the fuel would just be wasted, and that means you're burning more fuel and spending more money for less electricity. And that's where the real genius of modern power plant design comes into play.
The first major upgrade is called superheating. It's pretty much what it sounds like. Once the water turns into steam, you just keep adding more heat. This makes the steam way hotter and gives it a lot more energy to push on those turbine blades. The more heat you can add, the more efficient the cycle gets. But there is a catch. The metals in the turbine can only handle so much heat, and they usually top out around 600 degrees Celsius.
All right, the next upgrade is reheating. This is super clever. See, as the steam goes through the turbine, it loses energy and cools down. So, what do? You send it back for a boost. After it goes through the first high-pressure part of the turbine, the steam is sent back to the boiler to get heated up all over again before it goes into the next sections. It's like giving it a second wind, which gets you a much higher power output.
And this next trick, preheating, it solves two problems at once. Before the water even makes it to the boiler, it's preheated using a little bit of hot steam that's been siphoned off from the turbine. Now, this recycles heat, which improves efficiency for sure, but it also does something else that's critical. It helps get rid of dissolved gases like air from the water, and those gases can cause corrosion that damages the expensive boiler over time.
So what's the result of all these upgrades?
Well, it's pretty dramatic. A basic plant might waste most of its fuel's energy. But as you can see here, with superheating, reheating, and preheating all working together, a modern plant can reach an impressive efficiency of 40 to 45%. That means you're getting more electricity from every lump of coal, which is better for the environment and for our wallets. Now, generating all this power doesn't come for free. A modern plant also has to be a master at managing its byproducts. And we're talking about huge amounts of waste heat and, of course, the pollutants from burning fuel like coal. Remember this step? Condensing the steam back into water is the key to making the whole cycle work efficiently. To do that, you need a constant, absolutely massive supply of cold water to soak up all that waste heat from the steam. And that brings us to one of the most iconic structures you'll ever see at a power plant:
The cooling tower. Its job is actually pretty simple. It takes the hot water from the condenser, sprays it into the air inside that huge tower, and lets evaporation and air drafts cool it back down. Then, that cooled water can be sent right back to the condenser to do its job all over again.
The other major challenge, especially for a coal-fired plant, is dealing with what goes up the smokestack. When you burn pulverized coal, it releases pollutants that you absolutely cannot just vent into the atmosphere.
To solve this, plants use this amazing device called an electrostatic precipitator, or ESP. It basically works like a giant magnet for dust and ash. The exhaust gas flows past these plates with a high-voltage static charge, which zaps the tiny pollutant particles. These newly charged particles then stick to collection plates, kind of like a sock sticks to your shirt when you pull it out of the dryer. The plates get cleaned off and all those pollutants are safely collected.
The result is that the exhaust gas that finally leaves the stack is dramatically cleaner. This is what allows these massive plants to meet some really strict environmental standards. It's a critical piece of the puzzle for responsible power generation.
Okay, so let's put all the pieces back together. We've gone from a simple little 4-step loop to this highly complex, highly optimized system.
What's really important to get is that a modern power plant isn't just one single invention. It's more like a symphony of many different technologies all playing together, from the multi-stage turbines and advanced boilers to the efficiency-boosting heaters and the environmental systems like the cooling tower and the ESP. They all have to work in perfect harmony.
This incredible machine is a cornerstone of our civilization. But as our world's demand for energy just keeps on climbing, it leaves us with a final question to think about. How will these complex, powerful, and absolutely essential machines have to change and evolve to meet the challenges of the future?